And take a look at this. This is the compound interest formula that we probably first saw in our Algebra 2 classes, okay? This is for interest compounded a finite number of times. And this is the amount in your account after a certain number of years, okay? So P is the principal, R is the interest rate as a percent, and written as a decimal for the formula. N is the number of times interest is compounded in a year, and T is the number of years. So this is our compound interest formula. And I think this is pretty standard, probably the first application of an exponential function that we've all seen. And a pretty standard example of this is when we let the principal be $1, the interest rate be 100%, which as a decimal is 1.00, and T equals 1 year. And if you do that, then the formula becomes the following. Oops, it should be a 1. Okay, and usually the exercise goes like this, right? We use our calculator and we increase the number of compoundings in 1 year. And when you do, you'll find that this approaches the natural number E, we called it. Okay, for this reason, we in calculus, we actually define the natural number E as this limit. And we'll actually prove that later on in the chapter. But for now, we're going to use this, and it's based off of our previous work in pre-calculus. Okay. All right. So here's what I'm going to do. In this formula, I'll write this in red over here. I'm going to let H replace the fraction 1 over n. So that as n goes to infinity, the value of H is going to approach 0. And so I'm going to rewrite this to get the following. Okay, and I can get that, gang, right? I can get that from here. If H equals 1 over n, then n equals 1 over H. Okay? All right, now, if I remove the limit symbol from this, then the equal sign becomes an approximation. As long as H remains very small. Okay, so good approximation, as long as H is very small. Okay, I've removed the limit symbol. So, and I removed it so I can do a little bit of algebra. Okay, and I'm going to raise both sides to the H power. Then I'm going to subtract 1 from both sides. And then I'm going to divide out the H from both sides. Okay, and again, so I just manipulated the expression. This is a very good approximation. This fraction is very, very close to 1, again, as H remains very, very small. Okay, so this suggests that if I put the limit symbol back, my approximation should become an exact value. Okay, so it's a very interesting limit, I think. And why would anybody care? Well, if I wanted to find the derivative of the natural exponential function e to the x, assuming we don't know it yet, we would apply the limit definition. To get this. And I can factor in e to the x out of this using properties of exponents. E to the x, in fact, here, I'll write it up here. E to the x plus h, this right here, is the same as e to the x times e to the h. So I can rewrite my numerator by factoring e to the x out. And in this expression, the only thing that's changing is the value for h. E to the x is not changing. It's the h's that are changing. So e to the x, in a sense, is like a constant. I'm going to set it aside. And that is that rather clever limit that we just evaluated up above, whose limit or value we say was equal to 1. And so therefore, we get it's a kind of remarkable thing, right? What we found is that the derivative of the natural exponential function e to the x is itself, okay? Now, of course, we needed that very clever limit to figure that. But in the end, the derivative of e to the x is e to the x. We can show later also that if we were to make a composition out of it, the result would be itself times the derivative of its exponent, okay? A proof of that will come later. But for now, just to give you an idea of how special the derivative of e to the, or actually the natural exponential function really is.